Okay, thank you very much. First of all, thank you for giving me the opportunity to speak here and really for organizing this fantastic conference in a place like Hamburg, which is exciting to be back here, actually. So Ron just pointed out to me that this may be the first string theory talk at the String Math Conference. That's not obvious from the title, but Ron heard this talk already last week at Sheldon's birthday. Anyway, so I'll talk about N=4 super Young-Mills with varying coupling. You may all know what N=4 super Young-Mills is, but you might not have heard what it means to have it with varying coupling. So I'll explain this, and I hope at the beginning I'm a little sort of very, very slowly pedagogical, and at the end I'll sort of take off and do some physics with it. This is work in collaboration in various combinations with Benjamin Assel at CERN, Chris Cousins, Craig Laurie, Daria Martelli, Jenny Wong, and Timo Weigand. Craig is somewhere here in the audience, I don't know where. So these are postdoc students, and Dario is at King's, Timo at CERN. So as I said, we'll start with something that we should all somehow be familiar with. So N=4 super Young-Mills has had a lot of sort of, activity for various reasons. It's a superconformal field theory. It's maximally supersymmetric. It's sort of an extremely beautiful theory. You can study it from various points of view. Today we're interested in its SL2Z duality. So let's take this theory with a gauge group G, and then it has sort of an SL2Z monotone Olive duality, which generalizes electromagnetic duality, which acts on this complexified combination of the theta angle and the gauge coupling G. So tau is this object here, and the SL2Z acts as A tau plus B over C tau plus D. Under S duality in particular, G actually maps to its Langlands dual group, which has sort of generated a lot of interest in this theory in math. Now, I will need a little bit more information about this theory than just, this very sort of general statements. So I want to look at the theory for G=to U1. So it's an abelian theory. And just sort of say a few things, what are the ingredients in that theory, which will become useful later on. So the action is, we have this tau1, tau2, which are the real and imaginary parts of this complex tau parameter. They appear in the action in front of the star f wedge f term, and the theta term in front of the f wedge f. F is the field strength, here in this case it's abelian. And then there's scalar fields and fermions. And the abelian theory, that's basically all there is. So what's important is going to be what are the symmetries of this theory. Apart from the gauge symmetry, it has sort of the Lorentz symmetry in 4 dimensions. So think of it as SU2 times SU2, like in the last talk, for example. And it has this very large, the maximal SU4 asymmetry. So this will act on the supercharges of that theory. And in particular, I can now write the fields and the representation of this group, the Lorentz group, and the asymmetry. The gauge field is a vector and trivial under the asymmetry. The scalars are trivial under the Lorentz, and then a 6 in the SU4. And the lambda, lambda tilde are fermions, the vowel spinners, and transform in the 4 of the SU4. Likewise, this theory actually is, of course, as I said at the beginning, it's supersymmetric, and the supercharges transform in very similar representation to the fermions given here. So what we'd like to do today is look at this theory and think of compactifications of that, particularly on curves, where we allow this parameter tau to vary. So normally you would actually look at tau as a constant object, and then you look at sort of the dual theory, again with constant tau. I think that's the power, is it? Well, anyway, let's leave it. If we run out of power, we'll be fine. We'll. Okay, so normally tau is constant, and today we'll ask what happens when tau actually varies. So the first thing, it'll be very important to make sure that's consistent with the SL2Z, this duality symmetry here. For example, if we have tau goes to -1 over tau, say we do some loop in space-time, then it undergoes a monodromy like this, then in fact, this needs to sort of be compatible with the SL2Z. And to actually make this sort of happen, it'll be very useful to think of tau as actually a geometric object, namely as the complex structure of an elliptic curve. And for you who have heard talks about F-theory, that'll be very familiar. So we think of tau as sort of really a geometric quantity. There's an elliptic curve that's now fibered over the world volume over the n equals 4 space-time, and that's geometric. It's the complex structure of this elliptic curve. So why is this sort of something interesting to look at? So in string theory, we actually think of 4n equals 4 coming from D3 branes. So the low energy effective theory of D3 branes in type 2b 10-dimensional string theory is exactly this theory, 4n equals 4 sub Young-Mills. And actually, the type 2b string theory has a very similar duality symmetry. So there's an SL2Z, which acts on this tau 2b, which is a complex combination of the axion C0 and essentially e to the minus phi, which is related to the string coupling. And the type 2b string theory has a self-duality under this SL2Z operation on this tau 2b. Now this SL2Z descends on the D3 branes exactly to the Monton-Olive duality of n equals 4. So actually realizing now in type 2b these D3 branes and generalizing type 2b to actually a varying tau type 2b version, meaning F theory, the D3 branes that we consider actually also will have to have a description in terms of a theory that's n equals 4, where we now allow the tau to vary. So there are two setups that are useful to sort of keep in mind, and I'll discuss only one of them in this talk here. The first one is where we have a 4-dimensional space-time, where now tau varies over the full 4-dimensional space-time. And then there's a second setup where we say, well, let's put this n equals 4 theory on a complex curve, and tau only varies over the curve, and there's a transverse 1,1 dimensional space, and we're looking at a 2-dimensional theory on that space. And we're trying to characterize now, depending on what the variation of tau is, what the curve is, how it's embedded, what the 2-dimensional theory on R11 is. And we'll see it's a superconformal field theory, has 0,4 supersymmetry, so there are lots of things you can do with it. Okay. So this is motivation for string theorists. Why would you actually look at these D3 branes? So usually in F theory, we would consider some compactification on Calabi-Yau, say Calabi-Yau 3-fold or 4-fold or even 5-folds now. And we have some base, a bisection of this elliptic fibration. And the curve C, which appears here, is in the base of this elliptic fibration. So above this curve C, we have a restriction of this elliptic fibration to C, and this will induce the varying of the tau parameter of the n equals 4. So in 6-dimensional F theory vacua, these are 1,0 superconformal theories that have been classified recently in this beautiful work by Heckman, Morris, and Baffa. These types of wrapped D3 branes on curves inside the base of Calabi-Yau 3-folds actually sort of the smoking guns for saying these are superconformal field theories. So they're extremely important objects there. They also feature in 2-dimensional F theory vacua. So you can actually put F theory on a Calabi-Yau 5-fold, elliptically fibered, and then you get a 2-dimensional 0,2 model. And there you actually are forced to have these kinds of D3 branes for tableau cancellation. So from the physics, these are good motivation to look at them. Just formally asking the question, there's this SL2Z duality, can I now have this, can I use that to actually have a varying tau over the world volume of a D3 brane is a perfectly fine, totally F theory detached question to ask. So this is essentially just to back this up from F theory. So you should keep in mind for the rest of the talk, this is sort of the setup. There's an elliptically fibered Calabi-Yau. The elliptic fiber restricts to the curve C. The D3 brane wraps on C times R11. And the elliptic fibration will have a section, so it has some Weierstrass form. And F and G here will be determined in terms of the anticanonical bundle to the 4 and 6, respectively. And the elliptic fibration restricted to C will tell us how the complex coupling varies over this curve C. So the question that I'd like to ask is, what's the theory of these wrapped D3 branes in this 2-dimensional R11? Meaning, what kind of 2-dimensional CFTs are these? And can we calculate interesting physical quantities for them and, do the usual things that physicists do with conformal field theories, namely do some comparisons. For example, what I'll show you does some interesting new ADS dual solutions. Yep. I will show you exactly. It's not Waffer-Witten, so it's something that's a modification of the standard Beshatsky et al. Twist. So I will actually now get to the twist. So you can't just do the normal topological twist, because we'll see the supercharges will transform under this SL to Z. So there's something that's called the duality twist, and I'll get to that. Okay, the plan of the talk is we'll start exactly discussing that, how to actually define that N equals 4 theory. There's going to be a useful sort of 6-dimensional point of view coming from M5 brains, where you really take literally in the geometry this tau as an extra direction in your space-time that'll help us understand certain effects due to the singular fibers here. And then finally, I'll discuss sort of duals in terms of ADS CFT of these theories. Okay, so let's start with actually defining what these theories are. So D3 brains, I said, we'll be looking at this theory. It's N equals 4 super Young-Mills with this coupling. These are the symmetries. This is sort of the content. And we'd now like to pack this theory on a curve times R11 and preserve supersymmetry. So the classic way of doing this has appeared many, many years ago in this paper, Beshatsky, Johansson, Sadov, Waffer, and also then later in Kapustin, Witten. What we have to look at is the Lorentz group gets reduced. We have an SO11 acting on the R11 transfers, but also there's this U1C factor, which is the holonomy of the curve. So the spinner, so as we're looking at the supercharged Q, say, the spinner 2,1 will decompose into these two guys here. And we see that under the U1C, they have non-trivial transformation properties. So as we walk around the curve, these supersymmetries are not really constant. So actually, we need to do what we physicists call topological twist. So we also decompose the R symmetry, which is an internal symmetry, into an SO4 transverse times a U1R. This is the 4 bar decomposes in this way here. And now we can redefine what we mean by the U1C by sort of twisting it with the U1R. So define a generator T twist as the linear combination of the U1 generator TC and TR. And under this now twisted symmetry algebra, which is this index here in the back, we now have 4 chiral left moving and 4 chiral right moving supersymmetries, which are invariant under this redefined twisted U1C. And so we would say this resulting theory is a 2-dimensional 4,4 supersymmetric CFT. Or it preserves 2,2 supersymmetry, and you still need to check what kind of theory it is. And what's well known is the BPS equations of this theory along the curve are exactly the well-known Hitchin equations. So FZZ bar minus the commutator of the phi z bar is 0. The important fact here is that the scalars become now 1 forms along the curve after this twisting. So we repeat sort of the same analysis for the scalars, which were transforming in the 1, 1, 6. And then they actually become sections of the canonical bundle on the curve. Okay, so the resulting 4,4 supersymmetric sigma model is into a Hitchin moduli space MH, and this is sort of what came out of this analysis here. So this is not Waffer-Witten, this is a slightly different thing, right? It's more like Kapustin-Witten. So what actually changes when we now have this varying tau? So the supersymmetries actually transform under SL to Z. Say we have some element gamma in SL to Z. And the supersymmetries Q and Q tilde pick up a phase rotation. So this phase here is given in terms of the phase of C tau plus D. And so here these would have charge plus minus a half. And also the fields, except for the scalars, the fermions and also the gauge field combination given here, transform non-trivially under this SL to Z. So this means if we actually have tau varying over our space-time, we actually need to account for this as well. So in fact, not only do we have to do this topological twist of U1C with U1R, but also this phase rotation, which I'll denote by U1D, with the U1R. And this is what we call the topological duality twist. Essentially what this means is that all the fields are not just now, so the scalars are not just sections of Kc, but actually sections of this restriction of the elliptic fibration, so this Kb inverse to the curve C. So the sections of a line bundle that sort of characterizes the varying of the tau. So the connection is precisely given in terms of the tau1 over tau2. So this is 0 if it's just a standard constant tau n equals 4 super mils, but in general this now actually is non-trivial. Okay, so let's just quickly repeat how the analysis that we did earlier, sort of this recap from the 90s, how that changes. So in addition to the Lorentz and the asymmetry, we now have this U1 duality. The supercharges are charged +1 and -1 in a certain normalization. So if we have a curve C, say in the base of an elliptic Calabi-Yau 3, then we have the standard decomposition that I showed you earlier of the Lorentz and the R-symmetry, but now we have to not only twist the U1C with U1R, but also we have to twist with the U1 duality with the U1R symmetry. And the effect on the supercharges is now that actually the theory sees this to have 4,4, it actually becomes a chirally supersymmetric theory. So it used to be in the sort of constant tau setup, these guys were also trivially charged under the twisted U1s, but here you see these are charged under this U1D twist. So actually we were left with only these ones here. They're plus chirality in 2 dimensions, so we get 0,4 supersymmetry. Okay, now you can repeat this for different Calabi-Yaus. The interesting thing is always there are chiral theories, so you can get 0,8, 0,4, 0,2. You can also get 0,6. In all these cases, these involve this duality twisting and correspond to n equals 4 super Young Mills wrapped on curves in the base of these Calabi-Yau, elliptically fibered Calabi-Yau end folds. Sorry? The fields transform under the SL2Z in this way. That's right. Now I take this, That's right. So I actually, so think if this is the curve C, here there's a singularity of tau, so there's a monodromy around this point, an SL2Z monodromy. Then what I'm doing is I'm undoing this. I'm saying I would like to have scalar supercharges by twisting it with this R symmetry here. So this is the only way you can actually. So all it does is it ensures, so for the abelian theory you can do it explicitly in the action, or you can modify the theory. All it does is it says now everything is still well defined. The fields, the supersymmetries, as you do these monodromies. Right, so tau will undergo the duality, whatever A tau plus B or C tau plus D. And then the supercharges will remain, these ones with this twist here will remain invariant. We can actually, hello, Clay. So another way of seeing this, Craig, is you could also, and I'll get to that in a second, this is the same as just a standard topological twist of the M5 theory on an elliptic surface, like an MSW string, but on a very specific surface, which is an elliptically fibered surface. Okay, so we've looked at the supercharges. There's still a question is now what is that theory? So first of all, we could say what happens to the scalars. Before I said in the standard topological twist, they become sections of Kc. Now, if we follow this through with this additional duality twisting, the twist charge along this for this U1C twist still says, this interprets the field as sections of Kc, but actually, if they have non-trivial twist charge under this U1D twisted, they become sections of this line bundle LD, which is just a restriction of the anti-canonical bundle to the curve. Right, so this is the effect of the elliptic vibration restricted to the curve C. This is sort of telling us how much this coupling is varying there. Is the question? So for example, a field 211 here, actually this should be 11, is now a section of NCB by adjunction. So we can write down the full spectrum and organize it in terms of the 0,4 supersymmetry. The thing you should take away from this is each one of these charges here will tell us what kind of sections or what the multiplicities of these fields are. As I said here, these are now sections of KC and LD. So this is for the abelian theory. We get these sort of multiplets for the 0,4 hyper-twisted hyperfermis and the vectors. So anyone who's sort of thought mildly about elliptic vibration will say you forgot something really essential, namely elliptic vibrations are usually have interesting loci where the fiber becomes singular. So if we have a Weierstrass model, so we have a section, then the singular loci are sort of given in terms of the vanishing of the discriminant, delta for FQ plus 27G squared. In terms of F theory, these are the 3-7, so the intersections of the 7 branes, or the wrapped loci of the 7 branes, excuse me. So delta is the locus where the 7 branes are wrapping. So in our setup, there was this curve C. Generically, there's an elliptic fiber above it that's smooth. But now the locus delta will intersect the curve in points. So these are divisors in the curve C, above which delta is vanishing, and so the fiber becomes singular. Now, what happens above these loci is that the fiber is now not just some smooth torus, but some singular elliptic fiber. So some Kodaira fiber, for example, something like this sort of collection of rational curves. So from the point of view of our n=4 theory that's wrapped on this curve C, at these points, there will be some specific monodromies of tau that are dictated by what kind of singular fiber there is. And so as we encircle these points, we'll undergo some SL2Z monodromy. And so these loci precisely are what you would call a duality defect. So at intersection C with delta, at these points, there are additional localized degrees of freedom, which are so-called 3-7 strings. Okay, so before I go and discuss more what these 3-7 strings are and how we describe these theories, there's sort of one question that we should get out of the way, which is what replaces what used to be this sigma model into the Hitchin moduli space. So if we just had constant tau and we compactify with this twist I explained earlier, the n=4 on the curve times R11, this becomes a sigma model into this Hitchin moduli space. So one question is now what replaces this? So the BPS equation actually along the curve C, they become now something that looks almost like the Hitchin equations, except that this curly F is now this combination here. So A and A bar are the gauge field components along the curve, and these covariant derivatives are with respect to this connection, this duality connection, this UND connection. So both the scalars, these phis and A, are now sections of, if you ignore this for a second, KC and LD. And in addition, these loci here now will also say that there are additional sort of contributions from these discriminant loci. So all in all, what replaces the statement about a Hitchin moduli space is that here the 4n=4 with compactification and topological twist, which is the duality twist, becomes a sigma model into some sort of duality twisted Hitchin moduli space. So this is as much as we know. So since last week, this page already has improved by talking to Ron and Sheldon. But there's a question, what actually are the solutions? What really characterizes this moduli space here? There's sort of a very vague, but maybe sort of, slightly motivated thing that I'd like to say about this. So the S-duality really acts on the Hitchin moduli space as T-duality on the Hitchin fibers. So we could also say that maybe these maps from C to this Hitchin moduli space, they're now, or the Hitchin moduli over this curve C, they really should perhaps be thought of as we move on in this curve here, there's this defect, there's some walls that separate various regions of different sort of branch cuts for this tau, it's possible that we could think of this as now we have, as we go around a point like delta, we actually do a Tduality in this Hitchin fiber. I would love to understand this better. This is as much as I can say about it, but this certainly would be an interesting thing to look into, how the sigma model actually has a nice description using this information that the S-duality really is just the mirror symmetry on this Hitchin moduli space. Okay, so as a physicist, what can I say about these theories? First of all, in this picture here, you saw these walls. So I would like to explain what they really are. So this is where tau sort of undergoes this monodromy. So if we cut this curve up into these regions, Ci, and think of tau as, say, it has a single locus at this delta, then usually we would have, say, some behavior like log delta is equal to 0. So say if this is equal to 0, then actually the behavior would be log z of the axis of this tau parameter. So there are branch cuts now. So the action of the n equals 4, I can write it in terms of f wedge f dual, where f dual is this combination here. And then along these walls, where the branch cuts of tau are, I can write an action on the wall, which is essentially just making sure that the n equals 4 theory on this 4-dimensional space, C times R11, is well defined when I have a branch cut along W. So this is something like a mixture in Simon's theory, and there's not really a lot of interesting physics on these walls. What is interesting are these defects. So this is where exactly we have additional modes coming from 3/7 strings. They are the loci C dot delta, so naively you would say they're actually, delta is in class 12 C1b, so there are 12 C dot C1b, many modes at these locations. If we have a smooth Weierstrass model, we'll find out this is actually not true. So there's some subtlety in how exactly we should be counting these modes. This is sort of the naive thing, assuming that all the components of discriminant are essentially mutually local 7-branes. This is actually not true. So actually the right way to look at this is to go to a 6-dimensional point of view, where we now really think of the n equals 4 superangles with the varying tau as some full 6-dimensional theory on an elliptic surface times R11 and study it from that point of view. So this is essentially saying that we're looking at an M5 brane on elliptic surface, and then these 3/7 defect modes will actually come from a dimensional reduction on this elliptic vibration. Okay, so that's what I'll discuss next. And this also will answer, hopefully, Greg's question about whether this topological twist makes sense further directly. So the 6-dimensional 2,0 theory is sort of this unique superconformal field theory in 6 dimension, has some ADE gauge group. And one important sort of relation to low dimensional theories is, of course, if we put it on an elliptic curve with complex structure tau times R13, it just becomes n equals 4 superangles, where the coupling is tau. So our generalization of n equals 4 with varying tau translates conjecturally into, we're looking at a 6-dimensional theory now on an elliptically fibered space, where now the variation is encoded in the elliptic vibration. So the D3 brane wrapped on this curve C now becomes an M5 brane wrapped on this elliptic surface C hat times R11, and the C hat essentially encodes already the variation of this coupling. So if we do a dimensional reduction of the M5 brane theory on such elliptic surfaces, we should be getting the same theory as in the D3 brane case, and we should be also be able to actually describe directly what these defect modes are, since here everything is completely geometric. Okay, so one nice sort of fact is this slightly strange duality twist. Here is now just a topological twist on a Kähler surface. So C hat here is an elliptic surface. There's a standard topological twist that we can do, and then if we apply that this is actually elliptically fibered, it just reduces to this topological duality twist. So in fact, this also is the argument why this would hold for the non-abelian theory as well. So it's less clear actually in the n equals 4, where we can actually do this duality twisting only for the abelian case. Okay, so just to give you some flavor of why that is true. So the 6-dimensional theory is, it lives in 16, so Euclidean SO6 Lorentz and an R-symmetry SP4. They are in this superconformal OSP6/4, the bosonic part of that. And the abelian, so it's a single M5 brane theory, has this field content, which is fermions, again in 4,4 under this group, scalars, and the self-dual form. So B is a 2-form, and dB is self-dual. And the equations of motion are very, very simple. And now what we can do is really dimension reduce this theory, again doing a topological twist where we replace this SO6 now with the specialization to an SO11, this is the R11, and a U2 for a Kähler surface. So doing all this, actually, well, let me skip most of this. Once identifying what the topological twist is, we can really see that indeed this is the twist that in 4 dimensions would reduce to the topological duality twist I defined earlier. So from that point of view, you can also argue now that this twist makes sense. But the nice thing is really the 6-dimensional point of view is giving you really an angle how to discuss these two defect modes. Right? So naively in the sort of type 2b point of view, we said C dot delta should count the modes. As we'll see in a second, is actually not true. So the important sort of insight is that we can reduce this self-dual 3-form field along 1,1 forms of these special fibers, these Kodaira fibers in codimension 1 in this elliptic fibration. So we expand this field, impose the self-duality, and these give us chiral modes, which are exactly these defect modes. And doing this counting properly, we can account for these. And this the rest of the table is the same as I showed you earlier, but the additional piece which comes from these additional modes are 8C1 of B dot C. So this is actually the right contribution of these defects. Yes, so it's a smooth Weierstrass model. You can also include additional singularities. That will change the count. Well, in M3 you can always resolve this, right? So here, I'm not just drawing this because I like to draw these in this way, but actually you can really resolve this and look at that, resolved phase, and then in the reduction you're going to the n equals to 4 type 2b version of it. So in this counting here, this really assumes it's a smooth Weierstrass model. So all you have is I1 fibers, but if you had more, you would get additional half Fermis here. Okay. So what a physicist would now do is you have a 2-dimensional 0,4 theory, you compute the central charges. Actually, earlier I might have forgotten to say this is a 0,4 theory with a small superconformal algebra, and so the central charges here are now given in terms of intersection numbers of the curve and C1 of B with C. And this actually is also syncs well with sort of earlier results by Malsena, Strominger, and Witten, and Nasian Moore, and I think Timpis, who actually looked at related sigma models now for the M5 brane directly, reduced on a generic Kähler surface. Okay, so the important point about the 6-dimensional perspective is that we have an angle how to calculate this contribution from the defects. So this is already accounted for here. And now we can actually ask, so what can we do with the central charges? Before we get to this point, let me point out one other thing. If we had an n equals 4 theory where we now allow decoupling to vary over full 4-dimensional space-time, that would correspond to an M5 brane wrapped on elliptic threefold. In that case, these defects are now curves, and these curves can intersect. So we have these two-dimensional chiral defects in the base here, and they can intersect now in points. So you actually, if you now look at sort of what this self-dual field B does along these curves, essentially there will be a relation between the chiral modes on one of these defects with the modes on the other one. And that's essentially dictated as to how the Kodaira fibers behave as we go to these higher codimension singular loci. So that's essentially one other feature, that here you have sort of network of these duality defects that can have intersections at points, where from a physics point of view I actually get whatever flavor symmetry we had here from the Kodaira singular fiber, and flavor symmetry here enhances at these points. You get enhanced flavor symmetry. Another way of saying this is you have these chiral CFTs along these defects, which now have sort of point-like intersections. Okay. So I said we could calculate central charges. You can do this for Calabi-Yau 4 folds, where you get a 0,2 theory, and Calabi-Yau 5 folds as well. But the central charge calculation, if you look at this expression here, this is for still a single M5 brane, or the n=4 super-Yang-Mills theory with gauge group U1. And we'd really like to know how to do this more generally. Now, both the E60 theory as well as the duality twisted n=4 with variant coupling, we don't know really how to access this. As a physicist, you then would say, okay, is there maybe sort of another way I can get an angle to describe these theories? And so this will lead us to say, well, perhaps there's sort of a holographic dual which characterizes the same system. So there's some gravity solution, in this case an ADS3 solution, that characterizes the same system, where we can also calculate the central charges and match these with what we found here. So that's what I'll talk about in the next sort of 15 minutes. But let's take stock for what we've done so far. So we discussed n=4 with g equals to u1. There we have a complete description of this duality twist. We computed the central charges, meaning the spectrum, and the BPS equations are these duality twisted Hitchin equations. So they should be giving rise to some sort of sigma model into this, the two-dimensional theories, or some sigma models into these duality twisted Hitchin moduli spaces. And so one useful point of view is the E60 point of view, which tells us how to calculate the defect modes from the 3-7 intersections. But indeed, this is sort of limited to the abelian setup. So one question is indeed, how do we actually extend this, say, to NM5 branes, or SUN or UN n=4? And for this, I'll actually utilize sort of holography. So I actually write down for you a solution that characterizes exactly this brane setup, but in the limit, when we have sort of a very large rank gauge group. And so we have a dual description in terms of a dual string theory or supergravity solution. And so this is this work here in collaboration with these people. Okay, so just in one slide, what is ADS CFT? In fact, I think it was mentioned in the maths talk already, but let's just briefly recap. So we have a superconformal field theory in D dimension, then the dual holographic dual setup is a D+1 dimensional ADS spacetime, or in fact supergravity solution, which, say for n=4 super-Yang-Mills, happens to be this ADS5 times 5 type 2B superstring theory or supergravity. What's the point of this is that we can sort of access certain things here, so at weak coupling, and here dually, we could calculate these as strong couplings. So there's a strong weak coupling duality, but certain protected quantities we can calculate on both sides and try to match them. And this is sort of what we'll do here. So our setup is a two-dimensional conformal field theory. So we'd like to construct an ADS3 solution. And the only sort of caveat is that we have this varying tau. So usually we look at n=4 super-Yang-Mills. In this case, it's just a, say, vanilla and ADS5 times 5 type 2B supergravity solution. here we have this varying tau, and that'll actually enter into the construction of the solution. So what is the solution that we'll find without sort of writing down the metric and everything? So it's an ADS3 solution. It has an S3, which captures the asymmetry of the superconformal field theory. So it's a 0,4 small superconformal field theory where the asymmetry is exactly the SU2 acting on the S3. And then the compact space is an elliptic Calabi-Yau 3, and that's elliptic Calabi-Yau 3 where the actual type 2B solution is a solution AD3 times S3 times this base surface B4. For those of you who've seen these solutions before, if you put constant tau, then in fact this reduces to the standard AD3 times S3 times K3 solution. So here in the type 2B supergravity, there's an actual non-trivial profile for the axodilaton. The flux for the solution is given in terms of the scalar class of this base manifold B2 of the scalar, and this, of course, if we require this elliptic vibration to exist and be Calabi-Yau, the base B2 is constrained to be del pezzo by Fn or Boabdorov or an Enrique surface. And as I said, for constant tau, this is just becoming an AD3 times S3 times Calabi-Yau 2 solution. Now, of course, we don't write down an actual metric for this elliptic vibration. So in fact, this will give us some small sort of puzzle in a bit. So the supersymmetry is sort of realized in terms of there's a 2 of the SU2R that acts on this S3, and this is exactly telling us there's an R symmetry, which is SU2 of a small superconformal algebra. We can also actually orbifold this S3 and retain the 0,4 supersymmetry, and that will correspond to having additional, for example, for gamma, this orbifold group being ZM, additional KK monopoles, just as an aside. Okay, so we said we'd like to actually calculate the central charges of this. So the central charge is in this holographic setting is actually computed in leading order in this large parameter, the rank of the gauge group, by just a classical gravity result. So the left and the right central charges are just given in terms of effectively the volume of the base times 6n squared. So the volume of the base now sits in this elliptic vibration over here, where now, even though, say, this is a smooth wire stress model, there are singular fibers here, so there are I1s located above this base. So the metric on B2 is in fact singular. So we can't really use the metric to calculate this volume, but we can sort of calculate this volume by, say, just thinking of this in terms of a divisor in this Calabi-Yau. It's a section, in fact, and just sort of pulling back the Kähler form of the base. So doing this, in fact, the leading order central charge just becomes, so this volume of B is then just given in terms of half C dot C, is the leading order is 3n squared C dot C. Then sort of we can continue. The subleading term can be calculated from the couplings, the Chern-Simons couplings of the 7 branes. The CL minus CR is then 6n1 of B dot C. And if you all put this together, then the holographic result gives us this combination here. So the left and right moving central charges are given in terms of this expression. And n squared is still this rank of the gauge group. So now we can compare that with what we got for on the other side in the field theory from the spectrum calculation of the n equals 4. There we had the result for n equals to 1 now, n being this parameter here. If you compare these two things, these two leading orders, they agree, and at subleading order, there can be corrections now to the left moving charge, right? Because there's this additional constant piece. There are also other cross-checks that we can do, like looking at the fiber anomaly polynomial and comparing that to the anomaly there, which also then gives the same as this result in this holographic setting. Huh? That's right. So there's actually, okay, I can show you the expressions, but there's a 1/n thing that's, okay, we can discuss it in the, so, right, so actually one important thing that Clay's actually pointing out here is these behave like they scale with n squared. If you're familiar with the center charges for the 8 is 3 times is 3 times k3, these have a very different sort of behavior to these. Okay, so that actually, so we've completely rushed through this anyway. So let me just summarize. We've found these two-dimensional CFTs from the right dimension reductions of n equals 4, so pairing most with varying tau. For g equals to u1, we can have sort of a complete description of all these using either description in n equals 4 or in 6 dimensions from the M5 brane by dimension reduction. To go beyond this, the only way at the moment we know how to do this is to go to a holographic dual description, calculate the central charges there, and that then conjecturally computes them for a UN gauge group at large n. The nice upshot here is that we have this new holographic sort of framework where you have solutions of type to be supergravity where the tau parameter, this axodilaton, is allowed to have a non-trivial profile over the compact part of the space-time. And in fact, there are solutions also which preserve 0,2 supersymmetry of the same sort of type. One sort of interesting math question is what actually characterizes now this duality twisted Hitchin moduli space that I talked about in the first part of the talk. So we have not only contributions from this duality bundle, but also these modes from the defects. So this combined system gives now some modification of this Hitchin moduli space. So it would be very interesting to understand what exactly is that moduli space. Is there, in fact, a description using this action of the S-duality in terms of Tduality on that target space? Okay, so thank you very much.